Welcome to problem 4. We are grading some proofs here and hopefully the solution here will be short. So basically, clearly n squared is not less than or equal to n, and let's plug in an example. So n equals 1 works for this particular case, but let k equal to 2. So then 2 squared, we're following this proof with 2. 2 squared is less than 3 squared minus 1 is less than 3 minus 1 equals 2. This is what the proof claims, and we can see that clearly something went wrong in this step. 8 is not less than or equal to 2. What happened? Well, we can see here that isolating this inequality, adding 1 on both sides, and we see that this inequality is what we're trying to show in the first place. So this proof is wrong because we use something that just isn't true because we were trying to prove it. So, moving on. Now we have another incorrect proof, which is that 7 to the n is clearly not equal to 1 in all cases. And basically we should try an example in the inductive step proof. So let k equal to 0. 7, 0 plus 1 equals to 7, 0 times 7, 0 over 7, 0 minus 1. And you can see here that this is 1 times 1 over 1 over 7, which is actually 7 and not 1. So what went wrong? Basically, when we were taking this inductive step, we relied on an old subproblem, 7, 0, which we proved to be correct. But what happened here is that we haven't proven 7 to the negative 1 to be equal to 1 as a base case. And this is clearly not the case. So we can't rely on cases we haven't proven. So this induction fails. We needed a foundation, right? We needed a foundation, so suppose at the bottom are the base cases. And well, it's supposed to be straight, but for illustrative purposes, I've slanted it a little. So the base cases are k minus 1 and are negative 1 and 0. And so this is 1 minus 1 and 1 minus 0, which is 0 and 1. And you can see how they build up. But since this negative 1 case isn't proven, then we can't build up using the base cases, and so this induction doesn't work. Let's move on. And this is problem 4c. This problem is actually a bit more subtle than the previous problems. Now let's see what's wrong. The base case actually looks fine, and the inductive hypothesis looks fine too. But notice in the claim, you have for all x, y, and n in the naturals. So then x, y, and n must be greater than or equal to 0. Now, if we want to prove that for all x and y, max of x and y is equal to n plus 1, then x is less than or equal to y, this step looks fine, right? Because we're just supposing this if part. But the next step is where the problem happens. So max of x minus 1, y minus 1 is equal to n. Now, suppose either x or y is 0. This can happen because x can be greater than or equal to 0, and y can be greater than or equal to 0. And in fact, it actually happens in the base case over here. So basically what happens is if x is 0, without loss of generality, max of x minus 1, y minus 1 equal to n, this will be a negative number. So this will be -1, which is not in the naturals. So you cannot use your inductive hypothesis because you have this part in the claim where all x, y, and n have to be from the naturals. So that is what is wrong with this proof. It's actually very subtle. And with that, let's move on to problem 5.